This is a lecture for Friday, the 3rd of April. This begins chapter 30, section 8, which is all about inductors. We're going to just skip over. I won't bother presenting section 7 from chapter 30. Those are 3 applications of Faraday's law. It's pretty interesting. As a little hint, I might suggest you have a good read through those and brush up on those applications in case one of them pops up on the final exam. So for this section, the whole section is covered in pages 857 to 861. I would say that before you start going through this, read at least page 857. It just kind of gives the lingo about inductors. So a capacitor is something we studied at length, and it's a useful circuit element because it stores energy. And the energy it stores came from the potential energy of a battery, and it's stored in the electric field. An inductor is a circuit element, which is important, and it stores energy in a magnetic field. So your capacitor stores it in the electric field. The inductor stores it in a magnetic field. An inductor, and I've got some pictures here, it's really just a coil of wire, so it's the same thing as a solenoid. An ideal inductor, and of course most of them are real, but we can get kind of close to ideal. An ideal inductor has no resistance. So if you ask where does the energy come from, where does the potential come from, it comes from induced potential. So that's why we're doing this part after we've covered Faraday's law. The circuit element symbol of an inductor really just looks like a little solenoid. I'll draw the best I can now here on my trackpad. So something like this. I'll post a better picture with the notes. So that's what it looks like when we draw it in a circuit. A capacitor has capacitance, so inductors have inductance. The symbol for inductance is an L. And we know capacitance is related to the ability to store energy. There it's related to the charge and the potential. Here the inductance is related to the magnetic flux, phi m, and the current through the circuit. So that's our definition of inductance, and we're going to relate that more, of course, to what the stored energy is. The units of inductance are called henries, over the guy who studied this. Henries. This is pretty hard to write. A henry has a symbol of a capital H, and it has the units of flux, which are teslas, times meters squared, because flux is B times area, divided by the units of current, which is amps. Okay, so there's a brief recap of page 857. The next thing we're going to do is find the expression for our inductance L. Let's find something useful we can work with.